Thank you. I will, donuts. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray you bless this class. Help us to, again, Lord, glorify you in what we do, Lord. In your name I pray. Amen. I guess I should pray for King's travels as well. But he'll be here eventually. Okay, so I think I had advertised, one of the things in Calculus 3 that you might find a little bit mysterious is this claim we make that the partial xyz, partial uvw is equal to 1 over partial uvw, partial xyz. Now the question is, what does this notation mean, right? So typical Calc 3 notation for this, what this means is this is a notation for the determinant of a particular 3 by 3 matrix of derivatives, right? So this comes up and changes. So like this is x sub u, y sub u, z sub u, x sub v, y sub v, z sub v. I don't know why I'm not doing this for 2 variables, because I could illustrate the same idea with 2 variables and it would have been like significantly less writing, but you know what, that's kind of a preview of the rest of today, I think. I sad to say, but that's this. But on the other hand, this one would be this one. And so, from a Calculus 3 perspective, it might kind of seem like dark magic that these things should just be reciprocals of one another. But for us, we can understand it in terms of the chain rule. Let me show you why. So really, what we're talking about here is some sort of transformation, let's say from R3 to R3, just to keep things, technically there's fine print there, but and so maybe we're talking going from R3 with UVW to the R3 with XYZ, And so we're saying T transformation of UVW equals to what? Equals to X, Y, Z. And these are all functions, right? Of U, V, and W. But on the other hand, we have T inverse of XYZ is equal to UVW, where UV and W now are viewed as what? Functions of X, Y, and Z. There are problems in Calculus 3 where it is simply atrocious to solve for one or the other set of variables. And like a substitution naturally suggests itself, but to invert the substitution is a royal pain. And yet you don't have to if you know this thing, because you can just take the reciprocal transformation like this. It'd be better if I had an example right off the top of my head, but unfortunately I don't. So getting to the point. What's the composite of T? T composed with T inverse, right? Is the identity, right? Which means that the differential of T composed with the differential of T inverse is equal to the identity. Well, the differential of the identity, but that is the identity again, because the identity is linear transformation, right? And then the determinant of dt times the determinant of dt inverse. Well, fine, I'm sorry. This gives me then the matrix of dt times the matrix of dt inverse is equal to the identity matrix. I'm sorry, the matrix of the identity transformation, which I usually call IN. I do want to make a distinction between those objects here, right? So the Jacobian matrix of the transformation and the Jacobian matrix of the inverse transformation, they're they're inverse matrices, right? Given that they're inverse transformations. And so then you can take the determinant, right? And determinant product is product of the determinants. So there you have it. See, because now it's just a question of understanding the interpretation here. Because see, this is the determinant of dt, you know, and this is the determinant of dt inverse. And so that's why we have this reciprocal relation for the Jacobian factors of the forward transformation versus the inverse transformation. I really wish I had an example from Calculus 3 where it's horrible to not know this. It came up last semester of its own volition. Sam remembers. I don't remember off the top of my head. Well, he remembers it happens. I'm not putting it on him to tell me what the example was. That would be cruel and unusual. But okay, so this is one thing I wanted to mention to you guys. There's other kind of just a small theorem here, right? Which is that if f inverse is equal to g, right? And f and g are differentiable, right? Then, of course, we have that the differential of f inverse, well, I'll write it this way. The differential of g is equal to the differential of f inverse, which is more annoying if I write it this way, aka the differential of f inverse is equal to the differential of f inverse. But this is a straightforward consequence of just differentiating f composed with f inverse equal to the identity, right? So just differentiate that. Fouché differentiated, of course. And the chain rule tells me that's df composed with df inverse is equal to the identity. Because the differential of the identity is the identity. But if we have the composite of two transformations as the identity transformation, that says that they're inverses. Of course, we have the opposite. I mean, to be safe. Well, not sure I actually need that here, but just to be utterly pedantic and to try to hedge my bets for infinite dimensions. There you go. I mean, in finite dimensions, if I have a left inverse for the matrix, I have a right inverse for the matrix, right? I mean, like, for linear transformations in finite dimensions, if it's a left inverse, it's automatically a right inverse. This we know from linear algebra. But that is special. So that's kind of a neat little theorem, right? Other semesters I've made this a homework problem, but since I didn't for you guys, I thought I should cover it. Yeah. Now, Sam, you asked an interesting question, which was, it seemed like I was trying to get you guys to use the continuous differentiability theorem to solve a problem where it didn't apply. So let's see, I'm trying to remember what it was. I think it was, I was trying to get you guys to calculate like partial f, partial xij at a for f of x equal to exponential of x, right? Where x is a...
I think the one I was asking about might have been for fx equals x.
Oh, okay, there as well. Good, also fair. Or, but the same complaint can be levied against me because I was inviting you to make the following logical argument. I calculate the partial derivatives. I look at it. I go, aha, continuously differentiable. The derivative, the partial derivative is continuous. Consequently, the function is continuously differentiable. Then by the theorem, it implies differentiable at all such points.
The theorem's only for Rn.
But the theorem's only for Rn, right? So what I wanted to invite you guys to think about together with me is we've proved the theorem for Rn to Rm, right? What's that theorem? Let me remind you guys. Theorem. We have f, domain of f, subset of what was it, Rn to Rm. Then if f continuously differentiable, right? Can't spell. It's getting worse. Continuously differentiable on open U. Well, it's just on U, which is open. Then f is differentiable on U, right? Now to prove this theorem, I had to pick a path between the point and the point plus h that involved the stair stepping in n dimensions. We applied the mean value theorem on each little subinterval of this hyperparallel piped, and through judicious application of the mean value theorem, we're able to prove this, right? But it was for Rn to Rm. So my question is, and this is a true theorem, theorem we'd like to have is that f, well, let's say G, domain of G, subset of V, a normed linear space, to W, another normed linear spaces, normed linear spaces, listen to me, from one NLS to another, okay? Then if G is continuously differentiable on open U, then G differentiable on U, right? I mean, I've asked you to use this theorem. Maybe we should think about how to prove it.
Do we just pick like a norm that makes this easier to use the upper theorem?
Kind of, sort of. I think that's a bit of it. Let's say V is the span of beta. Let's say W is the span of gamma. Here beta, we'll let V1, V2, Vn. Gamma, for our convenience, we'll assume is W1, W2, Wm, right? Let me draw a picture. So here's V, here's W, right? F takes us from here to here, rather G takes us from there to there, right? But the theorem we know about is down here, right? We know about this theorem down here for F that's continuously differentiable from Rn to Rm. So I guess with drawing this picture, how do I get from the normed linear space V and the normed linear space W back down to where we have results? Using phi, which is the what? Coordinate mapping, right. So to get down from V, this would be phi sub beta, right? And this one here would be phi sub gamma. What is F in terms of G? I mean, what F should we think about, probably? Phi gamma composed with G, composed with phi. I once won second place on a graduate student poster contest, having the wrong order of a composite in a diagram prominently figured in my poster. Many technical professors walked past it and saw nothing wrong. I mean, I saw nothing wrong. I should put it in my office. It's fun.
Tell her story.
It was intentional, yes, of course, no. I mean, actually, I was like looking at it like a month later or something. I'm like, oh man, come on. But yeah, it's easy enough to get that wrong is my point. But we shouldn't. There's really no excuse. So I pick a point right here, let's say, B. And then what is, yeah, I think we're backwards. I think what we want, I think we want a phi beta inverse.
Oh no, I'm sorry.
And it's okay, I've forgotten who to blame. Because then if I phi beta inverse, like this, right? Then that takes me up to here. G takes that point over to here. And then phi gamma finishes the trip back down to there.
Sorry, that was my fault.
It's fine. Now, the beautiful thing here is that what can we say about the coordinate maps? In fact, this is a homework problem, right? Phi beta and phi gamma are differentiable. In fact, they're differentiable with differentiable inverse. Their inverse is also differentiable, and continuously so. I mean, these are pretty nice. They're linear, these coordinate maps. They pretty much destroy no information as far as we're concerned. So the thing is, if I have U up here open, you know, what do I have down here? So like phi beta of U, right? So this is going to be open. So to start with, I've got the right kind of, because it's a continuous map, so the inverse image or the, anyway, in fact, this is what's called an open map. It takes an open set to an open set. I'm not going to belabor the details in here. The point is that that's open, so I can apply the usual mean value theorem, right? On this, well, that's the question. If I have that G has continuously differentiable partial derivatives, does that imply that F has continuously differentiable partial derivatives? The question is, if we calculate partial F, partial UI, right, where I'm saying that this Cartesian coordinate UI, U1, UN, the Cartesian coordinates on this set down here, calculate partial derivatives with respect to that coordinate system, right? In other words, this is D, if I look at the point P, this is dFP of EI down there, right? But that's D of phi gamma composed with G composed with phi beta inverse, so P, EI. I think we can work through it, and we can prove that the continuity of the partial derivatives, I think we can prove that the continuity of the partial derivatives of G transfer to the continuity of these partial derivatives. I don't think it's immediately obvious, but I think it could be shown. All right? And once you have that, you apply the theorem that we did prove down here. You get that F is continuous, you get that F is differentiable. Once you know that F is differentiable, it's a simple matter to argue that G is differentiable because G is equal to phi gamma inverse composed with F, composed with phi beta. So if F is differentiable, then G is the composite of differentiable maps, which is once more differentiable. This is how we steal. So the point is, it's not a great loss of generality to prove things on Rn to Rm, because if you know how to use the coordinate maps, you can lift results to normed linear spaces. All of the deeper theorems that you prove in Rn or Rm, you could filter through these coordinate maps to get the results on a normed linear space, at least in finite dimensions. Infinite dimensions, still true, but then you got to work with, you got to be more careful than I am, okay? In here. I seem to have filled 3 boards with this. Now we'll get to my actual lecture. Any questions? So what I'm really trying to get at here, guys, is you're free to use the continuous differentiability theorem. Continuous differentiable implies differentiable theorem in the context of either Rn to Rm or a normed linear space, and this is why it's reasonable. Oh, by the way, I never told 2 years ago. So here's the deal. 2 years ago, I spent like a full lecture on abstract linear algebra. All right. And I had homeworks on like finding matrix of abstract linear transformations and so forth and so on. And it was fun, but I thought, I don't think I'm going to do that again. But because I did that, we had talked a lot more about coordinate mappings, but we hadn't talked about this theorem. This was actually a problem on their first test. I had not proved, no one had thought to ask what you asked, Sam. And it just hit me while I was writing their test. Oh, how do we prove this theorem on a normed linear space? I was like, I'll put it on the test. Some of them got it. They actually did this and gave me, they didn't give me all these details, of course, but they had a fair amount of it. I was pretty happy.
That's because I should have done it first and then asked you.
Yeah. Well, if I was a better professor, I would have made it a homework problem, but oh well. All right, so next order of business. The inverse and implicit function theorems. And I probably shouldn't say function. I should probably say inverse and implicit mapping. And the reason I say that is because I'm really talking about these results for functions that take their domain and range in terms of vector spaces. So I guess the first thing I always talk about whenever I bring up this lecture is I start by thinking about back in Calculus 1. And I think about the graph of a function, right? And then I ask the question, if this is y equals f of x, right? Then where can I find an inverse function? What do I mean by an inverse function for such a thing, right? So what would it mean for, so what we mean by that, of course, is the idea of a local inverse, right? So like, if I was to fix, between, say, here and here, I just look at this part of the graph, right? Suppose that that's, u. So I can say f restricted to u is 1 to 1, right? See, because there I have what? I have got f prime of x is greater than 0 for all x and u, don't I? I mean, the function's increasing right there, right? And so there, if I say, I'm going to say f inverse of y is equal to x, where f of x is equal to y, that actually defines the inverse function uniquely, right? Because if I had that this was f of x prime, well, that would say x is equal to x prime, right? By 1 to 1. So I can define the inverse function by just undoing the function, provided I have this injectivity of the function. But I get into trouble trying to construct an inverse as soon as I don't have 1 to 1, right? If I try to construct the inverse for the function after it goes over like a hill, then I'm in trouble, right? If I was to contrast a blue on blue, not so great. So if I was trying to construct an inverse function for this function restricted to like this, I get into trouble, right? Because if you look at this point and you look at that point, maybe we have f of 1 equals 1, and we also have f of 6 equals to 1. So when I ask the question f inverse of 1 equals to, well, is it 1 or is it 6, right? I can't decide. So we can't construct an inverse function if the domain we're looking at for the function doesn't keep the function injective, right? I mean, but if we can restrict the domain of the function, if we can look at a restriction of the function rather, then we can construct what's called a local inverse for the function, right? So what does this have to do with, what's the difference between the green, let's say U2? What's the difference between U2 and U1? Right, f restricted to U2 is not 1-to-1. That's the set theoretic comment. But what can we see in terms of calculus? Right, f prime of x is equal to 0 for some x in U2. That's the issue.
So we're considering f that are differentiable.
What's that?
We're considering f that are differentiable.
We always think about differentiable functions in here, yeah. Fair enough. Get that discrete math nonsense out of your head. Let's see here now. No. But yeah, that would seem to be the smoking gun, right? The fact that of course, the function's increasing, right? It's got this critical point, right? And then it's decreasing over here. So the fact that the derivative was non-zero almost everywhere doesn't matter. The fact that it was 0 at that one point, that's kind of death, right? So let me just talk for a second then about the problem of finding an inverse function. So what is the problem? We got y equals f of x, right? And we wish to find f inverse of y near, let's say, f of a, right? Where, let's say, f prime of a is not equal to 0. Again, I'm still thinking about a differentiable function just to get us started, because this is a good place to start. How do you actually find the formula for an inverse function? So here's a toy example, right? If I have y is equal to 1 over x plus 2. Suppose I want to find the inverse function. Suppose this is f of x, right? So what's f inverse of y equal to? It's actually equal to x, where we're saying solve this for x, right? Solve this for x, what do we get? X plus 2, 1 over y, right? Yeah, x is equal to 1 over y minus 2. Lo and behold, that is the inverse function of x. You got to free your mind of that garbage that they tell you in middle school about you take x, you take y, you switch them around, and you do this stuff that you don't understand. Right? Why do they tell you that? It's so that you can write f inverse of x. Because high school algebra teachers don't believe that you can understand a function of y. But we can. This is a function of the y variable. And that's the natural letter to use if we're using x for the domain and y for the range. The inverse function takes the range as its domain, so its input is y, and vice versa. Does that make sense? I think that makes sense. It makes more sense than arbitrarily flipping letters just so we can always work with functions of x. Sorry, my diatribe is done. Other questions? Comments? So you see my point here, and this is actually, I'm actually helping you guys with your homework problems. I've actually asked you to find the inverse function for some functions. How do you find the inverse function for a function? Same song and dance. If I have, x, well, suppose I have f of u comma v equal to, u plus v squared and u minus v, right? And I want to find f inverse of a comma b, right? What I do is I set this a is equal to a comma b, and what this is? What is it? You just take a equals to u plus v squared, and you take b equals to u minus v, and you take these and you solve for u and v stuff. Well, you know what? There's a nice notation for this. U of ab and v of ab. Don't tell the other math professors, but it makes sense. The reason I reuse u and v in this way is to avoid inventing yet another pair of letters. But what I'm trying to say here is to find the inverse function, just solve this for u and v in terms of a and b. Can you guys do it just to make this less abstract? I just made it up, so there's a great danger here that it's impossible. I can definitely solve for the v. I mean, I can get, well, curses. Did I say minus v squared? I meant minus v squared. There. Life is now good. Sort of. Or is it worse? Was it better without it? It was better? Oh. Oh yeah, we don't want that. We don't want that. So with this, let's see here. Curses. Yeah, solve this equation for u and v. Isolate u and v.
If it was v squared,
I think it might be better with the square.
It was better with this?
Yeah, v squared.
I might say that.
All right, we're back to the square. Let's see here. I'm going to regret doing this. Oh well, we're too far down. It's too far gone. We gotta keep with it. So solve for u.
That's a plus b divided by 2.
Oh, okay. So a plus b is equal to 2u. So therefore u is a plus b over 2. Very good. There's one down.
And then we use the square root of a minus b over 2.
So v, I guess you got choices, right? Oh, okay, I'm sorry. So v squared is b minus u, or we could say it's a minus u. Does it matter? Either way, that gets us back to what? I think either way we end up with what? B minus a over 2 for v squared? Oh yeah, thank you. I can't do math. A minus b, yeah, sorry. Uh-oh. Uh-oh. Uh-oh.
If you do a minus b
Uh-oh.
equals, a minus b equals
Uh-oh.
u plus v squared minus u minus v squared.
I'm in trouble. I'm sorry, I'm confused now.
If you do a minus
Yeah, but
b,
I'm sorry if you do,
if you have like a minus b,
yeah.
that's u plus v squared minus u plus v squared, I guess.
So we get 2v squared.
Yeah, so it's instead of being a minus b is 2v.
Okay, I'm sorry. I'm somehow getting confused. I don't know what's wrong with me. Let me just, there, better. So you got choices, right? So plus or minus the square root of a minus b over 2. Now we're going to have to commit to a plus or minus depending on where we're finding. The question is, which inverse are you finding for? It's just like over here, there's a local inverse for this side, there's a local inverse for that side. They're not the same local inverse. You know, those same issues come up here. But the idea is basically the same. You just solve, to find algebraically the formula for the inverse, simply solve the range variables. Solve for the range variables in terms of, how can I say this right? Write down range variable equals domain function, range variable equals domain function, and then solve for the domain variables in terms of the range variables. What I just did here. Okay, it's better. Now, obviously, that's going to be a pain in general, right? And we'd like to have a theorem which kind of tells you when it may or may not be possible. And so just to put the cart before the horse a bit here, and just to kind of forecast the trouble, this has, what's the Jacobian of f here? Right? And so that's what? 1, 1, 2v minus 2v. So the determinant of the Jacobian of f is equal to, what is it? It's minus 2v. Okay, phew. I was worried there for a second. So it's minus 4v. Great. What this says is that the Jacobian is invertible for v not 0. What the inverse function theorem says is that if you pick a point for which the Jacobian's invertible, all right, excuse me, if you pick a point for which the differential is invertible for the map, all right, and if the function is continuously differentiable in an open set around that point, all right, then a local inverse will exist about such a point. So this suggests as long as we stay away from where v is equal to 0, we can find a local inverse. Algebra has showed us in part what the trouble is with v equal to 0, right? V equal to 0 is the divide between the formulas. So like we can even see what's going on here. We're going to get plus the square root where v is positive. We're going to get minus the square root to get where v is negative. Never the twain shall meet. I mean, it doesn't have to be, though. Like it's fortunate for us that where the derivative is 0 actually turned out to also be a point where I can't find a local inverse. I think that that doesn't have to happen. I mean, the inverse function theorem, inverse mapping theorem just tells me that if the differential of the map is invertible, then there exists a local inverse. It does not say that if the differential is not invertible, then there's no local inverse. Unfortunately, that just isn't the case. We can already see that from the cubic function in the reals. So this function, right? So here f prime of 0 is 0, yet f inverse of y is the cube root of y. That's a global inverse despite the fact that we have 0 at that point. So a failure to meet the criteria of the inverse function theorem doesn't mean that there can't be found an inverse function. It just means we don't know. Okay?
Is that like one of those not enough information deals?
Right, exactly. So the inverse function theorem It's a forward direction. It's not an if and only if result. Yeah. Okay. Gotten things a little bit out of order today. So let me get back to my song and dance about y equals f of x, all right? Let's go back. I never completed this thought here, did I? And it matters because actually understand, this is the thing that's so beautiful, you guys, is if we can understand this one-dimensional argument, we can easily motivate the proof for the mapping theorem. It's fascinating to me, but it's that simple. So how do you, all right, this was an example. I was trying to get you guys on board with the idea to find the inverse function we solve for the domain variable, right? How do you solve for the domain variable y equals f of x abstractly, given it's differentiable? We linearize, right? We say y equals f of x, which is, to a very good approximation, f of a plus f prime of a times x minus a, right? And then to find the inverse, or a pretty good approximation to the inverse, what do? Solve for x to find nice approximation for inverse. So let's see here, solve for x. What do we got? Y minus f of a equals to f prime of a times x minus a. Remember, I assumed the derivative is non-zero, which, of course, I motivated from our initial discussion of what's a local inverse look like. So you solve, we get 1 over f prime of a times y minus f of a is equal to x minus a. So there you go. X, which we're going to, x is equal to a plus 1 over f prime of a times y minus f of a. So this is approximately f inverse of y. What assumption do I need to do that approximation? I just need one thing. I need that f prime of a is non-zero, which is the one-dimensional analog of saying the differential is invertible. Because a number has a reciprocal, it has an inverse, multiplicative inverse if it's non-zero. Does this look at all familiar to any of you? This thing we're doing? Any of you guys studied Newton's method anywhere? What? Yeah, Newton-Raphson method, yeah. So there, let's see here. It's very much the same kind of idea. It's just instead of solving, I mean, with Newton's method, we usually have y is equal to 0. We're trying to solve where f of x is equal to 0, right? So if you try to solve f of a plus f prime of a times x minus a equals to 0, that's usually what we give Newton's method. The first iterate would be, x is equal to, how's it go? Minus f of a. I can't do math. Minus f of a divided by f prime of a plus a or whatever. I'm sorry. There's something I'm missing. Let me stop that. So sorry. Something I'm forgetting. All right. Now that of course is not, that's an approximation for the inverse. So what do you, trying to think of how you take the next step. Goodness gracious, I'm just missing words today. Let me. So basically, the what if we have a function? We have a function from, you know, Rn to Rn. And we want to calculate, if we want to find an inverse function to it, right? At some point. So suppose, so what we do is we suppose that f prime of p, right? Which is, you know, in my current notation, that's an n by n matrix, is invertible. Then we can calculate the linearization of f at p is what? It's f of p, right? Plus f prime of p times x minus p. And so I'm saying that's equal to y. X and y are vectors. P is a vector. To find the inverse function, simply solve for x. How does that go here, though? It's almost the same. I mean, it looks like the same, right? But the difference is that this is a matrix times a column vector, is the difference of this column vector and these two column vectors over there. If the matrix is invertible, I can multiply by the inverse matrix on both sides, and we get x is equal to p plus f prime of p inverse, as in matrix inverse, times y minus f of p. This is the first step in an iterative procedure to finding the inverse mapping. Here, let me tell you. So here's how do you make the next step? So basically we're looking at, let's see, I need some language here. Well, I guess not. I've used A instead of P in the notes. Let me just change this. Well, I guess I can just, let me try to adapt the theorem 3.1.2, changing my A to P as appropriate rather than vice versa. So we would have G sub 0 of y would be equal to P. So this is even before this. Like, what's the stupidest approximation you can come to? If you have, you know, if I have f, you know, f of p equals to b, whatever that is. What's the stupidest inverse function that would approximate this? It's just the inverse function, whatever you put y into it, it gives me back p. This is the 0th and most stupid approximation to the inverse. The first approximation I've got down here. So G1 of y would be, well, just what I wrote here, p plus f prime of p inverse times y minus f of p, right? Oh, for some reason, well, let me just rewrite this. So this is actually G0 of y, and I'll pull the minus out to make it look like the notes. Okay, guys? F prime of p inverse times f of, what was p? P was G0 of y minus y. So here's the iteration. The nth, so if you keep doing this, like, let's see, I'm sorry, guys, there's like a sentence I need to say here, I just can't think of it. But the next thing down the line would be, say, gn plus 1, which would be gn of y minus take the inverse derivative, inverse matrix of the Jacobian of f, and then multiply that times the column vector f of gn of y minus y, like so. This is that Newton's method that I can't explain worth anything today. Like, you know what you do, you keep applying it to zoom closer and closer to the 0. In the same way you keep applying this to get closer and closer to the inverse function. This is actually the iteration that does that for the mapping. Yeah.
How important is it to apply the negative to certain terms?
Oh, I'm just trying to make it look like my theorem 3.1.2. It's the same thing. It wouldn't really matter. Yeah. Here, I see at this point that calculus 2 has ruined my brain today. So let me phone a friend, a smarter me who wrote these notes at a point in the past. Oh, why am I, so for example, why am I looking for a adapter cord? This has an HDMI port. What's wrong with me? So many things. Let's see here. See, I'm not actually expecting you to work through this iteration for even one example. It is hopelessly technical. All right? But it's important to go through this because it's actually the basis for the proof of the theorem. The lowest order part of the proof is just what I said. You linearize the problem and you solve for solve for x as a function of y, and that gives you the inverse function. And then past that, you iterate. And I've actually gone through that a few years ago in this course, and it's not. I've drifted away from actually showing the details in lecture because it is rather complicated. But anyway, so here it is. If we have f from Rn to Rn continuously differentiable open set W containing A, and the derivative matrix f prime of A is invertible, all right, then f is locally invertible at A. This means that there exists an open set U containing A and an open set V containing the image of A under F, and a one-to-one continuously differentiable mapping G such that G is the inverse of F. All right? Moreover, this local inverse can be obtained as the limit of a sequence of successive approximations. So I've tried to start to explain, I think I've explained the first approximation to you. There's some sentence I'm missing to really make good on why we keep doing this approximation to get closer. But it's just like Newton's method. And so that's actually the proof that you can find in Edwards. He proves that this sequence of functions converges with respect to the limit of sequences of functions. In other words, that all that sequence, operator norm and function, the space, the norm on function space, it's quite technical. And but on the other hand, it's also very beautiful. It involves something called the contraction mapping, and it's definitely something that I don't think you necessarily need to learn for this course. But if you're a math major and serious about going to grad school, it'd be good for you to study it, like after you've had real analysis, to come back to this and try to like understand the proof of this. It would be a wise thing. But it is hard. But on the other hand, it's a very beautiful theorem. So in short, it's just like calculus 1, except instead of needing the derivative as non-zero, we simply need the Jacobian matrix is invertible. With that, we have an inverse, at least locally. Any questions? Yes, no, maybe so, no. There are refinements of this theorem. For example, you can read in Muncre's analysis on manifolds. He actually, I think, he has a rather different proof that doesn't use contraction mapping. It's more topological in nature. To give you an idea what I mean by that, one of the things you might wonder in this theorem is I assume that the the differential is invertible at a point. And I also assume that the function is continuously differentiable. The mapping is continuously differentiable. You'd be like, well, doesn't that mean that the derivative is, like the Jacobian matrix is invertible, like on an open set containing that point? In fact, it does. Like if the function is continuously differentiable, you can't have the Jacobian matrix is like invertible just at that one point, but then close to it, it's not invertible, because the inverse image of open sets is open. I mean, it goes back to that continuity of the determinant. See, here's the argument, actually. The determinant's a multinomial, the component functions of f prime of x. It's continuous, right? And we're given that the Jacobian matrix is invertible, which means that this is non-zero. And so we've got a continuous function which is non-zero at a point. But in calculus 1, we learned that if you have a continuous function which is non-zero at a point, right, there has to be an open neighborhood of that point on which the function remains non-zero. Continuous functions can't be non-zero at a point and then infinitely close to that point have a point where it's have it be zero, right? There has to be some neighborhood around the point where it's non-zero, where it stays non-zero. This intuitive observation is the heart of like the intermediate value theorem. But anyway, that obviously has little, if anything, to do with the proof I was starting to do over here, right? This iterative procedure doesn't use that idea. It just is basically doing Newton's method on mappings and just iterate, show that the iteration converges. There's hardly a lick at topology in that. Very different ways of looking at it, yeah.
You will be on the provable with the projection of f and g. I mean local.
U and, I'm sorry, U and V?
The u will be on the theorem of both is in projection by f and g, right?
Yeah, f of U is V, and f inverse G of V is U, right? And G would be the inverse of f restricted to U. Yeah. But there's greedier theorems still. If you look in other books, you can find a proof that if you assume that the function is not just continuously differentiable, but like r times continuously differentiable. In other words, the partial derivatives, the r-fold partial derivatives exist and are continuous. So you can keep partial differentiating, and all those partial derivatives are continuous. Then you can also prove that the inverse also is r-fold differentiable, continuously so. So you get in what you put in. If you have like CR data, you get back out a CR inverse. I'm not going to prove this, but it's known. And the proof can be found, I think, I think the proof might be in Edwards. I forgot. I have it here somewhere. I mentioned a source. But so what I'm doing in this example, we just went through for a simpler example, right? I just said, this is actually how you do it. To solve for, to find the local inverse here, I do that down here. I just take and solve A and B, right? I solve this for x and y. And so there it is. And here's some details, which I will get confused on if I try to talk about right now. But so this is the same song and dance we just did a minute ago. Solve for the variables to find the inverse. Up here is the application of the theorem. You differentiate the Jacobian matrix. The Jacobian matrix is this, right? When is it invertible? Yeah, we just need the determinant non-zero, which in this case is the product of the cosines of x and y be non-zero, right? So we need to stay away from like x plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2. And we need to stay away from cosine plus or minus pi over 2. I mean, y is plus, so any odd integer multiple of pi over 2 for x or y, there's a grid of badness, right? And so if you pick a particular rectangle in there, you can pick a point, and you get the existence of a local inverse in each grid, of which one the formulas for sine and are nice. As you know, inverse sine is a predefined function, and this is anyway. Enough about that.